Hello and welcome to the third video of the A-Level Physics Electricity series. Just a disclaimer that again this video is applicable for both GCSE and A-Level Physics students. Here are the contents that I will be going through in this video. I will be time-stamping every single area that I cover, and I would recommend you use these as prompts for your active recall for your exams. So let's begin. Let's look at the IV graph of the ohmic conductor. So firstly, with this graph, it doesn't matter if you have your current on the x or y axis and your potential difference, vice versa, because the graph of any ohmic conductor will always follow Ohm's law, in that it will always be directly proportional, and for a graph to show directly proportional relationship, it needs to have two things. It needs to be a straight line and it needs to go through the origin. An example of an ohmic conductor, because you could definitely be asked that in the A-level exams, are things like resistors or copper wires. Looking at the IV graphs of filament lamps, you can see that there are two different graphs depending on where the axes are. So if you've got the normal current on the y-axis and the potential difference on the x-axis, then it's going to look like that, it's going to curve like that. But if you swap the axes around, it's going to curve the opposite way. And there's often a 4 marker attached to looking at the IV graph of filament lamps. And the 4 marker itself is explain the shape of the graph. So what you would want to say is firstly establish the relationship between the current and potential difference by saying that the current is not directly proportional to the potential difference. And you want to say that the temperature of the filament lamp increases as the current increases. And this is because the resistance increases the collisions of the electrons or the charge carriers with the positive metal ions, and therefore that's overall can be summarized as a heating effect. So as the temperature of the filament lamp increases because of the current, this causes the resistance to increase, more collisions, and therefore it's not an ohmic conductor. But why does the temperature increase as the current increases? That's an interesting question, because in this question we talked about how the resistance increasing causes the temperature to increase. But why does the temperature cause the current to increase? So the current is defined as the rate of flow of electrons. Basically, how many electrons flow past a point per second. Now, the current causes collisions with the fixed metal lattice atoms, because the electrons aren't just flowing through an empty wire, they are colliding with the positive metal ions as they're trying to get towards a positive terminal. And therefore, this is resistance. It's opposition to the flow of current. The more collisions that it experiences, then the slower the current will be. Therefore, the greater the current, the greater the intensity of the atoms vibrating and collisions with the ions, and those vibrations then cause the filament to heat up because energy is being wasted. So the potential energy that's supposed to be used for the components is being wasted just by heating things and turning into thermal energy. So that's why it causes the filament to heat up. Now let's look at the IV graph of a semiconductor diode. So in the forward bias, which is the first quadrant, you can see that the current flows easily past the threshold voltage. Just a key thing here, the threshold voltage is the minimum amount of voltage needed for current to begin to flow. So the minimum pressure needed to push the electrons to start flowing. And beyond that point, current flows quite easily. But you can see in the next quadrant, it doesn't seem to work at all. And what's happening is the resistance of the diode is extremely high in the reverse bias. And that then means that no matter the potential difference, the current is not going to be increasing at all. Now, a diode or a semiconductor diode is an example of a non-ohmic conductor, because you can see that in the reverse bias, the resistance actually decreases with the increasing current. and also you can see in this part of the graph here. So as the potential difference increases, the current increases a lot more. And the reason why is to do with charge carriers. This is the potential difference, the current potential difference graph of a negative coefficient thermistor. Now those words are just excessive, it's basically just a thermistor, and it's going to be the opposite to that of a filament lamp. Again, because of the same reason as we saw in the diode, because the current starts increasing more than the potential difference is increasing, which is the opposite to the kind of resistance effect. And that's because the number of charge carriers increase. So we'll look at that in a second. But this is often a graph that's represented with thermistors. So which just displays that at a very low temperature there's very high resistance, and at a very high temperature there's very low resistance. That's the symbol for it. So let's look at why the current increases more than the potential difference increases. So hopefully here you can see a multimeter. And the multimeter is highlighting how the temperature is affecting the resistance. So what's happening is the current flow causes a heating effect, as we looked at, which because of the excess collisions that are occurring with the metal lattice, energy is being dissipated as thermal energy. The energy supplied causes more valence electrons, outer shell electrons, at the same time to become delocalized and move and carry charge. So what's happening here is, although energy is being used to cause the electrons to get congested and lose current, it's also causing the valence electrons to gain enough energy to move to the conduction band and start carrying charge. Now, if you're unfamiliar with the terms I'm using, I'll recommend you watch my first video where I explain all of that in baby steps. Now, because they are more electrons able to move and carry charge, and current is defined as the rate of flow of electrons, if there's more electrons, then that means that the net charge is increasing and the net current is increasing. And because potential difference is constant, the resistance then decreases and the current increases. So as you can see here, the higher the temperature, the lower the value of the resistance. So just an overall graph analysis of current potential difference graphs. This is an example of an ohmic conductor. And when they have a drawing of it in this quadrant here, you may be thinking, okay, I understand the current increases, potential difference increases, but how does this section of the graph make sense? Well, it just says that the negative quadrant, the voltage is traveling in the opposite direction. So you kind of switch the direction of the terminals on the battery. Also, the fact that there's a straight line through the origin, as I mentioned earlier, it highlights that there's direct proportion and that it is therefore an ohmic conductor. It can be a straight line, but if it doesn't go through the origin, that may have been because of human error if it was in an experiment. Things like zero error. The reciprocal of the gradient is the resistance. Why is it the reciprocal and not just the gradient? Well, you've got current on the y-axis, potential difference on the x-axis. So you're doing current divided by potential difference. But we know that resistance is equal to voltage divided by current, so the opposite way. So you have to do the reciprocal of the gradient. Unless you drew a graph which was potential difference on the y-axis and current on the x-axis, and then the gradient would just be the resistance. Now, I mentioned threshold voltage. As I said, it's the minimum amount of voltage required to which current can flow. So the voltage at which the device can switch on. Because remember, voltage is a pressure pushing the electrons and causing the current. And voltage, therefore, induces a current. But something I haven't spoken about is surge current. Now, surge current is basically the instantaneous input current drawn by an electrical device when first turned on. So it's basically when you turn an electrical device on and it suddenly draws a large amount of current. And whenever there's a large amount of current, that is very dangerous for us. It generates heat that can damage the electrical appliance. And if we were to get in contact with it, we could also die because very high current is very deathly. Thank you so much for watching. If you found this video and this series helpful, make sure you give it a like and share this series with as many people as you can. Also, I have videos on other A levels coming up as well, and subscribe for the GCSEs if you have any younger siblings or friends. Have a lovely day and best of luck in your exams.